In this tutorial, I'm going to be teaching you guys the basics of linear algebra. In order to do this, I'll be breaking these tutorials up into few separate videos. And in today's video, I will explain the most fundamental question of linear algebra, and that is what a vector really is. Now, from a physics perspective, a vector might be an arrow which has a certain length and direction. From a computer science perspective, it might be an array of numbers. But today we are going to look at it from a math perspective, and we will see how all these ideas connect, because mathematicians love to generalize things up. Now, to really understand this, we first need to talk about what a vector space is. A set V is called a vector space if it satisfies these 10 conditions. Now, if your head already starts spin, don't worry, these aren't super hard. They are just rules like any game has, just written here in a mathematical language, and I will explain all of these one by one visually. Note that here we are only going to talk about real vector spaces. There are lots of other kinds of vector space, but they all follows the same rules. Now, the first condition says the set must have a zero element. This is just like the number 0 in regular arithmetic. If you add it to any element, you get that same element back. Let's say this point here is our 0, and this red rectangular box which contains that 0 represents our set V, and all these points inside this box are the elements of V. The second condition basically says that for every element in V, there must also be an opposite element in V. Let's say here is our element alpha, then here is our negative alpha. But it doesn't contain in our box, so we would have to enlarge the box to make sure all those opposite points are included. Moving to the next point, the addition of two elements must contain in V. Now, don't worry, in the next video I will explain how we define addition in real vector spaces. For now, just grab the insights. Now let's pick two elements at random inside the box. If we add them together, sometimes the result ends up outside the box. To capture that result, we would need to enlarge our box again. But then what about this one? And this one? If we keep repeating this process, we will see to capture all possible additions, we actually need an infinite box with no boundaries. That way, every addition stays inside the box. The fourth point says that the order of addition doesn't matter. If we add beta to alpha or alpha to beta, the result will be the same. Choose two elements, then add them, and the result will be independent of the order. The fifth condition is associativity. Pick any 3 points and add second and third, then add the result to the first one. Alternatively, add first and second one, and then with the third one, the result will be the same. Now, sixth condition is about scalar multiplication, and again, don't worry, I will explain this in more detail in the next video. Basically, it says that if you scale an element, the result should still be in the set V. Since our space is infinitely large, all scaled elements stay inside it. And because this multiplication stretches or shrinks an element by some number C, that number is called a scalar. Now, conditions 7, 9 and 10 are kind of vacuously true. So I will leave those for you to think about. Pause and ponder how they work. Leave a comment with how you picture them. Moving to the next condition, it says if you scale two elements, then add them, it's the same as adding them first and then scaling the result. We can picture it like this. So, if a set satisfies all of these conditions, we call it a vector space, and all the elements inside that set are called vectors.